Добрый день, уважаемые коллеги. Я очень рад здесь.
Good afternoon, colleagues. It is a pleasure for me to speak at this forum. It's a wonderful event. We have a lot of information about windthrow events, not just the tornadoes or gales, but we also have information on non-convective storms and snowfalls. But today we will focus on tornadoes and squalls, on the windthrow events. We know that windthrow events, the standard replacing windthrow events in certain regions of the world are the main factor that damage the wood cover, and especially in Central and Eastern Europe, where Western and Central Europe, where it is the leading factor. And at the same time, as for Russia, until now, there were either local estimates for individual Russian provinces or groups of Russian regions, or these estimates were too general. There is the well-known publication of Potapov and his co-authors, and he made a presentation here yesterday, and they have estimates of standard replacing windthrow events for the European part of Russia. And probably that team of authors were the first to produce such an aggregate number, but we never had any detailed estimates. At the same time, the damage is growing everywhere, especially in Europe, in the European part of Russia. We don't understand what causes that change, probably because everywhere in Russia, the age of the forest is increasing. Again, we did not have much information until recently whether it's a new trend or an old trend, whether we have always had or there has been a trend of windthrowing events. Are the mechanisms in Europe and in Russia the same? The mechanisms of those events, is there any difference? We still could not tell. That's why we decided to make an overview of different findings that were produced in the last several years. The methodology focuses on the European part of Russia, and we will be using the data for tornadoes and squalls from several sources of data. Landsat time series, also Sentinel from 2016, and two products that are based on Landsat that Potapov presented yesterday. There is this product for changes of land cover in Europe and land use maps. We wanted to gather information about meteorological events that cause standard replacing windthrow events. So we used Met Station data, like the European database, the eyewitness accounts, and other Russian publications. There have been a number of them in the Russian Meteorology and Hydrology journal. And we also used weather satellites data in order to fine-tune some of the characteristics that we were using in our models. We try to monitor tornadoes across all of the Russian territory. But like I said, in this study, in this model, we are focusing on the European part of Russia. Over here, you can see information on land cover. And this is one of Sergei Alexandrovich's maps. That's one of Professor Bartolyov's maps. The methodology itself is quite sophisticated. And probably you can't read very clearly from this slide because it's too busy. So let me turn the page, and I will start explaining the methodology with a database. We have a database from 1986 until 2017, that's 32 years for the Russian-European part. And we had 3 types of objects in the database. The elementary damaged area, this is a Landsat database or Global Storage Exchange data. Then we have the windthrow area as a separate object. This is a damaged area that's collocated. Over here, you can see a chain of windthrow events which were caused by one storm, obviously. And our third level or object is storm events. In the European part of Russia database, there are about 700 windthrow events, and that can be classified into about 460 storm event tracks. We used global forest change data as our main source of information. We complemented it with Landsat images. Global forest change allowed us to understand the damages that have typical features of a wind-thrown event, the direction of the wind, a certain structure. And then we would group them into 2 types of wind-throw events, linear and fan-like. Linear, they're shown here at the bottom, they are caused by tornadoes, and then they're most frequent ones. And then we also used satellite data in order to confirm our hypothesis. We used public source data that provide information about the direction of the tree fall. Of course, we don't have long time series for those images. In our study covered a period of 30 years. So for the time when we did not have satellite images, we used indirect properties in order to understand whether this is a tornado or a squall. Those features are the character. If they are linear over here, it should be linear and it should have those slow curves, which is not typical for squalls, but it is typical for a tornado, that the turn in those curves, this curvature is quite soft, it's quite slow. So here you can see a good good example of a squall. Over here you can see a good example of a tornado. And we also managed to establish the exact dates for these events. Then there were also other events that we couldn't classify using global forest change or other sources. They are the windfall events that were covered by other events. We managed to uncover them because we had information about a particular date, about a particular event, or because we realized that a particular area could not have been logged. So if we saw something suspicious, something that could be classified as a logging area or a wind-thrown event, then we would be using the indices, using the last covered masks over here and the NDII. This is the Moscow hurricane that is very well recorded. On the 21st of June in 1998, there was a squall that caused a lot of wind-thrown activity in the Dimitrov region of the Moscow area. Global forest change data have a 1-year resolution. So it means that within 1 year, you could have both a wind-throw and a logging activity. And then we would match them with Landsat images before and after the event. This is how we did it. Before the event, after the event, same period of 2012, and we know about the event in July 2012. Some harvesting that happened before the windthrow were excluded, thus enabling us to keep in our records only the actual windthrow event. Of course, we still cannot exclude that there is still some error in the database, that we missed some of the harvesting areas and that we classified them as a windthrow event or the other way around. This is how we determine the geometrical parameters of the event. There is this width, side to side. There is the length. I think you understand how we computed the area. Next, the issue of accuracy. How do we estimate accuracy? Of course, it would be best if we could have high-resolution images. For this, we selected several windstorms. Some time ago, we did a separate estimate for squalls and a separate estimate for tornadoes. We vectored our past information along the high-resolution images. We delineated everything manually, and we realized that according to GFC data, for smaller windthrow events, the area is overestimated, sometimes by as much as 30%. We are talking about an area of 30 to 50 hectares. But in the case of large events, the case might have been different. It could have been opposite. The area would be underestimated. We are not the first group to have these results. In 2012, there was a publication that showed that Landsat satellite overestimates small area stand replacing windthrow events. Over here, you can see a typical squall, a windstorm. This is a water reservoir, and you can see how the forest was damaged in the coastal area. This is your typical tornado. The signs are really evident. The trees fall counterclockwise, because this is how your typical tornado moves. Over here, you can see those funnels, really, and this borderline, this frontier between not undamaged forest and total damage. Here you can see several more cases. This is the third category of tornadoes, EF3 tornadoes. This is one of the greatest tornadoes that we registered in the Arkhangelsk region. This is data from 2008, and this is from 2009, the Yaroslavl region. Another well-known event, there was a tornado which was caused by the same mechanism. Non-convective events can also cause a windthrow. The biggest event of this kind, the so-called VSIM, windthrow event, is a well-recorded case from the 6th of June 1995. There was a major snowstorm, and there was a lot of snow falling, about 70 millimeters of precipitation, and strong winds, 25 meters per second, and the windthrow was recorded at an area of 20,000 hectares. And there was also partial damage covering more than 300,000 square hectares. It was very well recorded and described in different publications, including international publications, but it is a unique event, and it happened beyond the Urals mountains, and that is why it is not part of our database. We never had anything similar in the European part of Russia. This is very typical for dark needle-leaf forests. They are widespread in the northeastern region of Russia and also in the Urals. In the Urals, you have another additional contributing factor, like precipitation. In this case, there was a major snowfall, and probably a combination of all these drivers led to this phenomenon. Now let's turn to the European to the European part of Russia data. Damaged area, 300,000 hectares of the damaged area, and you can see the distribution between windstorms and tornadoes. We have 295 cases recorded with a high degree of certainty, and we have almost 100 tornadoes in our database that were classified as such with a medium degree of accuracy. However, although we have many events of this kind, the area that they damaged is smaller than the area damaged by fewer squalls. Already in 1980s, there were publications on the tornadoes, and we confirm that data. These are long-lived storms that happened in 2010. These two windthrow events, and they are responsible for 38% of all area damaged in the European part of Russia over the past 30 years. The events were truly unique. In 30 years, nothing similar reoccurred. Here you can see the density, the percentage of damaged area out of the total forest cover, a 50-kilometer cell for tornado-induced and squall-induced. Over here you can see two false positives, while this area, this is the Perm region and the Komi region, the eastern part of Komi. There were several events here coming together, and this area could be especially identified as a reserve, and everything to the south of it, it is the zone that is most prone to large-scale windthrow events in the European part of Russia. Speaking about time distribution, our series is not homogeneous, and the growth that you observe here is artificial, but we can still see some characteristic peaks. There was a peak on recurrence of tornadoes in 2009, and there was another smaller peak in 2017. 2010 is the leader in the series of the devastating squalls that took place in that time period. Before that, we never set such records. 1993, 1996, yes, there were some events recorded then, but looking at this time series, we still can't be sure whether there is indeed a growth. We've filtered minimal areas with different thresholds of 100 and 200 hectares. According to all data, well, it's very difficult to find smaller windthrow events using all data. So we do observe some growth. We still can't claim that this is an objective trend, a definite trend. We're still not sure. Monthly distribution, as it should be expected, the maximum is in June. Non-convective storms usually happen in August. This is September, this is a snowfall in August. There was a cyclone, an unusually strong cyclone, which caused a gradient wind. The geometric parameters distribution show us the difference between tornadoes and storms in terms of their length. The longest tornadoes were 70-80 kilometers long, while that's storms, while tornadoes could be up to, I'm sorry, the tornadoes can be long, and the tracks can be up to 70 kilometers long, while storms can also be quite long. It doesn't happen very often, but there were cases recorded of up to 500 kilometer long tracks. This is distribution of wind damaged area in forests with various dominating tree species. Our data was of low spatial resolution, so it was difficult to compare. Here is a typical case: dark needle-leaf forests, and there we see a lot of damage. If the storm track encounters deciduous forests, the damage is less. The difference can be threefold. You can't say really that small-leafed forests are not affected, but they are definitely affected less. And these are the most severe events. There are 7 of them. Only 1 of them is non-convective. The rest of them, well, 2 non-convective events, because I also included the 1995 event, although that's not part of our database officially. They can produce a lot of damage. And next come additional data. This is what we managed to understand analyzing stands replacing windthrow events. Alexander Chernokulsky made this publication with a team. There is another publication to be made in the Russian Journal of Meteorology and Hydrology sometime in the middle of next year, where we will be sharing an updated map of tornadoes in Russia from 1900 until 2018. There are about 1,800 cases of tornadoes. 770 of those tornadoes were confirmed with satellite data. Obviously, this is information from recent years. 2017 is the best analyzed year, when we have most of the events in 2017 for 2 reasons. One, indeed, in 2017, we had a lot of tornadoes, and on the other hand, the technology improved, and now we have access to more detailed data. In order to work with this information, we need to establish intensity. Intensity is usually assessed based on damage that is caused by a windthrow event. For some events, we can estimate probable intensity. The probability, Viktor Chernokulsky suggested a methodology to calculate the probability based on the length and the width of the track. The idea is American, but it was adapted here, and as a result, we confirmed that some tornadoes, about 10 tornadoes in the European part of Russia that caused windthrow events, have an intensity of 3. They belong to category 3. And some of them are comparable to Ivanovo tornado, although we didn't know about them before. This is statistics. Again, lately, there's been growth, but this is artificial growth because now we have social media, now we have other sources of information, now we're analyzing satellite data with a high degree of accuracy and detalization. We also studied several events. The first one is the 1984 Ivanovo tornado outbreak, this is when Landsat 4, Landsat 5 went into business. We reconstituted tracks that were caused by this outbreak. Secondly, we also studied severe tornadoes and devastating squalls. The Ivanovo event. We calculated the actual length and width of the tornadoes. 2 tornadoes were confirmed for the first time. We never had information about them before. They were not part of the databases. We know the maximum length and width of the main tornado, and we also collected data for later periods, and we confirmed that several other tornadoes were comparable with the tornado, with the Ivanovo outbreak. Although Ivanovo outbreak is an extraordinary event, but it's still not unique for the European part of Russia. Tornado outbreaks. Now, the Tver outbreak, which was in 2017, holds leadership in this race. We confirmed 52 tracks of tornadoes. Some of them were the satellite tornadoes, so-called, but we used the American methodology of estimation, and on that basis, we confirmed 52 tornadoes in one day. We analyzed wind throw events using high resolution and Sentinel data. And another one, the 7th of June 2009, the Perm region and the Komi Republic, 20 cases, and some of them very severe. These 2 events after 1984 were the most prominent tornado occurrences in the European part of Russia. Storms, 2 events of 2010, on the 27th of June and the 29th of July. Both of them were caused by the periphery of anti-blocking cyclone, and in total they resulted in 37% of all damages caused by stock replacing wind throw events anywhere between 1986 and 2017. We started these activities using meteorological modeling. Over here you can see the visualization, the animation of this convective storm. And we also have satellite animation. This is clouds moving over the surface, and these 2 events were classified as derecho, long-lived storms that can survive for 6 or 8 hours and sometimes more, and at the same time they keep moving at a tremendous speed. In the past, this kind of events were never recorded in Russia. If you look at the length of the track, these events are 2 without precedent, and both of them happened in 2010, and they are both associated with the very well-known blocking anticyclone. There is also this comparison of the damage caused by wind throws and other impact factors. In 2018, there was a project for the Urals region, and we completed it then. You know that Urals it acts as a barrier. We know that big wildfires spread to the east of the Urals. And you can see clearly that the area in the Ural region is incomparable, and fires cause much more damage there than wind throw events. But you can take a look at the actual geographies. This is the meridian, and if you look at to the left, there is a big contribution of wind throw events, and it can be as high as 40% for some geographies. But if you look beyond the Ural Mountains, you will see that wind throw events contribute only 1%, maybe even less than 1%. You have 4 minutes left, including questions. Okay, I will do my best. So we calculated those maps for the forests of the Urals region. Conclusions. You can read the conclusions from the slides, and you can find more information in our publications. There are links on the slides, but there is also this portal that we have where we constantly update our data. There are 700 events that are already recorded there, but the 2020 events, for instance, are added almost in real time. This year, there were at least 5 very big windthrow events in the European part of Russia. The biggest one in the Arkhangelsk region in the area of Sura. It was one of the record setters for the decade. So you can go to this portal and download the data. And here are links to different articles. I think I should stop here. Again, these are our main publications. And thank you very much for your attention. Well, thank you. Thank you very much. That was an interesting presentation. You produced an excellent service. And like you say, you update the information regularly. It's wonderful. Thank you. Are there any questions? Well, our colleagues are thinking about their questions. May I ask you something? Professor Bartolov showed us their products, and you have your product. What about integrating your products? Like GSV maps, can they be combined somehow with your maps? Well, actually, we discussed that about a year ago, and probably it was slightly different context because we did not have the results that we have now. We were only planning to get them, but as far as I understand, we are mostly interested in understanding the contribution of windthrow into the disturbances and into the damage caused by different disturbances. And yeah, it's possible to get those, well, we have the estimates to tell you the truth. Now the only thing that remains to be done is to do the actual comparison. I think we'll do it in the near future. Colleagues, we still have like 1 minute left for questions. And if there is something that you would like to ask Mr. Shikhov. A question? Is there a question? Yes, Andrei. Is there any correlation between windthrow events and fires? That is to say, is the threat of fire higher following a windthrow? There is a lot of dead wood on the ground, there is a lot of dry wood. Probably it is a source of a fire risk. Do you have any comments about that? Well, I think that we should study big windthrow events. Smaller ones are usually cleaned. Sometimes this activity is so intensive, and it did intensify in recent years, that they're interfering with our research. Sometimes the area is cleaned so fast that we can't confirm the fact of a windthrow event. But yeah, I probably there is a region where we are tracing fires, like the Perm region and the neighboring areas. And until now, we have not identified any correlation. There is no interplay, or rather, there is no causality between fires and windthrow events. Wherever there are strong winds, there are, well, no, start again. Wherever there are windthrows, there are few fires. And wherever there are fires, there are few windthrow events. So it looks like, well, at least until now, we can't confirm a relationship between fires and windthrow events.